students, as you remember in our previous lecture, we developed an intuitive understanding of Taylor series by using a simple example from motion of a particle in a straight line. Now, in this video lecture, we will focus on formal derivation of Taylor's series for a function, for a real function of single variable. But before that, I want to tell you that whenever you look at this equation, this simple equation of motion, s is equal to ut plus 1 half at square, from now onwards you will remember that you are actually looking at Taylor's expansion. The question is how? Answer is because distance traveled by a body, as you saw in the previous lecture, you saw that distance traveled by a body is function of the time. So this you can write it ft, function of time, is equal to ut plus 1 half at square. Okay, now you see that this function of time is basically equal to, what is this u? U is the velocity, but velocity is f dash t, rate of change of distance is ft, so function, this velocity is f dash t. Now I can write here f dash t, but since it is initial velocity, this means that it is value of f dash t at 0 time. Initial means at t equal to 0. So I can write it f dash 0 into t plus 1 half. Acceleration, what is acceleration? Acceleration is this rate of change of velocity. Rate of change of velocity. 0, evaluated at t equal to 0 into t square. This is the rate of change of velocity. That is acceleration. Now, since the acceleration is constant, you can take acceleration at any moment, at any instant of time from say 0 to t interval. In 0 to t interval, you can take value of acceleration. So I have taken it at 0, value of acceleration at the start. Now I can write it, same expression can be written now as ft is equal to f dash 0, okay, and instead of t one can write t minus 0 plus 1 by 2, or simply we can write it f double dash 0 by 2 into t minus 0 whole square. One more thing lastly, that is ft is equal to there is no term here that is that would describe value of this distance traveled at 0 time. Actually, while we derive this equation, we assume that the body has not covered any distance up to t equal to 0. At t equal to 0, distance covered. What that means? It simply means that we start counting distance from 0 time. So whatever distance the body might have traveled before 0 time, we ignore that. But in general, we can have a term here that would represent value of distance traveled by the body at t equal to 0. That is fo plus, which in this particular case is 0, and then other terms f dash o into t minus 0 plus f double dash o divided by 2 into t minus 0 square. Now compare it with this fx. Fx is fo, fa. We had a instead of 0 in our example, plus f dash a again, t minus a plus f double dash a by 2 t minus a whole square. This is Taylor's theorem. So basically, whenever you now look at this, remember you are looking at a Taylor's series. Now let us go to now our next topic, that is formal derivation of Taylor's series. How to go for that. That is quite simple, very simple. Yeah, as you can see yourself, we start with this. Suppose we have a function gx defined in this interval a to x, from a to x. This is the interval including a and x. That's why it's closed interval. Now we will assume that the function is continuous in this interval, so a and is differentiable in this interval, both continuous and differentiable, and in fact it is infinitely differentiable. That is our requirement. That will be our requirement. But for the present, it should be at least one. It is first derivative should be defined in this interval. Okay, with these things, I start with this. I take this first derivative, g dash x, integrate that from a to x dx with respect to x, and I will get integral a to x. G dash is derivative of g with respect to x, that is dg by dx into dx. Dx will cancel, you get integral a to x dg, that is equal to integral. Now you know integral dg is g, this is gx, and these are the limits 0, a and x. So we have g a gx minus ga. This is called fundamental theorem of calculus. So according to fundamental theorem of calculus, the definite integral a to x of g dash x is equal to this. There you have g dash, you have g, evaluated at 2 points, x and a and x, and first comes this x, then comes this a. So we can, let us reproduce it on the other page. We have, what we have seen is integral g dash x dx a to x is equal to, that is equal to gx minus ga. We will do one more thing, that we will recast it in terms of gx. We will write gx on one side and other two terms on the other side. You see, if you transport this to this, then we will get g plus ga plus this is plus ga plus integral a to x g dash x dx. Okay, now having said this, I can write this. The same thing can be written as, what is this gx? Is a function, value of function at x is equal to value of function at x is equal to value of function at a, okay, and plus a to x g dash x, that is derivative. Now we have integral of derivative of fx into dx. We shall remember this equation in terms of this. Let's call it equation first, and we will write first here. We will be using this equation repeatedly, but because, and one more thing, that is, the function can be any function. It's not necessary that you will always have gx or you will always have fx. It can be any function. The function should be continuous as well as differentiable in the closed interval a to x. So if with that information, let us begin. Let's start with fx function, where function fx is equal to, according to, and apply this rule, fx is equal to fa plus integral a to x, derivative of fx is f dash x dx. Okay, now this is okay, this equation 2. Well, now this equation 2 involves another function, that is f dash x. This function f dash x is a function. Now this f dash x, fx is a function, so is f dash x function. This is continuous, this fx is continuous in that given interval and is differentiable. So is this, we assume this also is. In fact, let us assume that fx is infinitely differentiable in that interval, so that we can have f dash x, f double dash x, f triple dash, and so on. Now we have now this situation. We will use this equation first for f dash x. In place of function at x, we will write here, in place of this, here we will write this function f dash x. F dash x. Instead of previously we wrote fx, we will now write f dash x. Treat f dash x on the same footing as fx. So here will be f dash x, here will be f dash a, here will be derivative of f dash x. Derivative of, not now, it is not now fx, it is now f dash x. This function, derivative of that function, that is, as you know, derivative of the function is f dash x is not f dash x, rather f double dash x. So apply this rule, this fundamental theorem of calculus to f dash x. If you apply, you will get this f dash x here in this place is equal to, here now come to this, it is fx, f a, value of function at a, plus, but f dash a, sorry, the function is f dash x, so f dash a plus integral a to x, derivative of this function, derivative is f double dash x dx. Such is the, this is the equation. Now this equation, please remember one thing, that I have not actually, you may tend to think that sir has actually differentiated this equation. I have not differentiated this equation to get this equation for f dash x. No, rather I have got this equation third, let me write it, equation third, not from 2, I have got it from 1, fundamental theorem of calculus. I am not going to differentiate this and get this. If I differentiate this, you see, if I differentiate this, I will get f dash x is equal to 0. Here you will get 0. And here integral will go with differentiation. Now, this will be entirely different. Differentiation of this is entirely different from what I write here. I am simply using this function for f dash x. Next time I will be using the same function for f double dash x. Now, first let's substitute f dash x in equation second. Here I mean here in equation second, f dash x. When you now take when you replace this f dash x in equation second by f dash x, by this value, I mean this value, the equation will become, let's see, you see, first we have f x. I am substituting f dash x in equation second from equation third into equation second. So I will get, I have to substitute it here in place of f dash x. Rest of the two terms will be same, they will not be affected. This term fx and fa, they will not be affected. So I will first write these two terms. I will write fx is equal to fa. Now the next term, x a to x, Now let's go back. Now you have a to x, you have written that, and you are now going to substitute value of f double dash x. Sorry, you are going to substitute value of f dash x, this value of f dash x. So I will have to substitute this f dash a plus this into this equation 2. When I do that, I will get first of all this integral. See this integral. Rather, let me do one more thing. That is, let me reproduce this equation on the next page so that it will be easier for us to see, to check and see. So I will write fundamental theorem of calculus first on this equation. See, instead of this, let me first write this fx is equal to fa. This is fundamental theorem of calculus plus integral a to x f dash x dx. This was our equation 2. Okay. Now now f dash x is our f dash x equation is f dash a plus a x f double dash x, because now you have to substitute here derivative of this. There the function was fx, derivative was f dash x. Here the function is f dash x, derivative will be f double dash x into dx. This is our equation third. Now when I substitute this into this, be careful now about this. You have fx, you'll get fx equal to fa. These two terms will not be affected. Now this term will be affected. But before substituting f dash x here, what we do, we actually this put up some space for the coming value for this expression. Let us first make some space for that. What I mean that, let me write first this ax, and then leave a space here for these two terms to be accommodated. But let me not forget that there is something more with f dash x there, that is dx. What often students do, they ignore this. Now you are only going to substitute the value of f dash x here. You are not going to change anything else there. So when you substitute this value of f dash x here, I will first deliberately keep that value in these parentheses. Say I will write there which value I have to write here, value of f dash x. And what is that? That is f dash a plus a to x f double dash x dx, this dx into which dx this is this dx. Now you have two dx's. You can check it once again. Let's check it once again. What we have done, I have substituted here. I have substituted equation third into equation second. Third into second. So fx fa plus a to x. Then but first then dx, this dx that is there, and then f dash x is these two, and these two out of them, first is f dash a, second is itself having integral a to x f double dash x and dx. Now if you look at this term carefully, you will find that we have now two integrals, a to x here and two dx's. You can see it now. Going for the integration itself, I have fx is equal to fa plus a to x f dash a. Now you know that a f dash a is constant because f dash is second order derivative, but evaluated at a point that is called point A. So when you evaluate it at point A, it now is a constant. Had it been f dash x, then it would have been a variable. But it's not f dash x, it's f dash a. So it's a constant, you can take it out. F dash a integral. What is left here in its place? This dx. Or better for you, in an easier way, we can write it as simply as integral a to x, okay. Then f dash a. Then see, look at these parentheses. What you have outside is dx. So I will write here dx. This dx belongs to both this and this. So I have another this term of the integral, that is a to x, this a to x, this now is here. Again a to x, this a to x and this a to x, and then inside I have f double dash x dx. A few things are noteworthy. Number one is that you must keep track of this c. This is quite easy. This term is quite easy. Now go to this. We have integral appearing twice. That is, it is double integral. Okay. Now integral appearing twice, two times, and we have this derivative, second order derivative. This is second order derivative. These are I should say two order derivative. These are two integrals. These are two dx's. Sorry, I have forgotten one dx. These are the important things, dx and this dx. There are two dx's. 2, 2, 2. And now, writing it here on next page, first I will write fx is equal to fa. First, fx is equal to fa. Fx is equal to fa. Okay, plus back to this. Fx is equal to fa. Integral a to x f dash a dx plus integral a to x f dash a dx plus now the third term, that is third term is plus double integral a to x f double dash x double dx. Now a to x twice integral a to x, okay, a to x, okay, and then f double dash x, okay, into dx, or you can also write dx square. Well, that is okay. Now next, what we have now next, that is we have to apply now this fundamental theorem of calculus again, but now for f double dash x. And as we know from our this previous page, function at x is equal to function at a plus integral of derivative of the function into this dx. So I write it here. Function at x, function is equal to x, function at x, function at a plus integral a to x derivative of function of this, I mean this function func into dx. Okay, use now this fundamental theorem of calculus for a value of f double dash x. So you put the f double dash x here, and then you will have f double dash x at a, f double dash at a, because value of function at a, okay, value of function at a plus a to x, derivative of function, derivative of this function, that is triple derivative 1 2 3 into x dx, triple derivative that I have now I have actually used f triple dash x here, because I have to put derivative of this, whatever the function is here, I have to substitute this, it is derivative here. Well, good. Now substitute this in this equation. I write it fourth equation, in equation 4. Substitute this from fifth into fourth. Therefore, when you do that, therefore you get fx is equal to fa plus now f dash a, take it out, f dash a, and you have integral a to x. Why did I take f dash a out? Because it is constant. A to x dx, plus now that term. Since the term will become now large, so I don't have space here. I will rather write it here plus. First, it's two integrals that it already has: a to x, I mean this integral, and this integral, these two integrals, and just replace f dash x with this, but remove f dash x from there, leaving behind two dx's, dx into dx, or we can say dx square. Okay, now substitute this expression for f double dash x. So what is the expression that I'm going to substitute? That will be f double dash a plus integral a to x, derivative of function, and derivative of this derivative of function, that is this f triple dash x dx. Okay, now a little bit simplifying will lead us to, we will have fx is equal to let us see what terms we have, is equal to first term. Now first term is fa. So first term fa, we have actually written it here. Let us go back to second term. Second term is f dash a f plus f dash a multiplied by something, multiplied by an integral. And let us go back to that, multiplied by an integral. F dash a multiplied by integral a to x dx, multiplied by a to x dx. Now plus then plus, we have now this integral, double integral a to x, double integral a to x, and then inside that double integral we have this function f double dash a, f double dash a, then we have this in parentheses, this f double dash a, then next is plus a to x, again a to x plus a to x. Good. Then we have a to x, this is a to x f triple dash x dx into dx square, f triple dash x dx, f triple dash x dx. Now these are like this, and then we have dx square already that we had from the previous expression. You can check it. This was from the previous expression, dx square, and new is f triple dash x dx. So what I get, you can yourself see. Now I will simplify it a little bit. You get fa is equal to fa plus f dash a. Now integral dx, that is x. Now that is x, and then give lower limit a, upper limit x to this x. Integral dx is x plus you have plus integral a to x, integral a to x. Okay, f double dash a, sorry, f double dash a, I have f double dash a. See, this f double dash a has with it this dx. It also comes with dx. This dx actually this I should not have written here. This I should have written it here. This dx is common of this and this. If you then take this dx, take its let f double dash a take its dx separately. You have f double dash a into dx plus the last integral, the last one, that is f, this ax. Okay, into third ax f triple dash x dx, that is dx cube. Once again, what you find is that you have triple integral 3, triple this derivative 3, triple dx. Okay, now we need not go for now further this substitution, other things. We simply can now easily understand that. Likewise, we will have, if we continue, we will have ultimately this is one thing remains. There one thing remains. You see here x then with limits this. This means that this term will ultimately become, give it x value, x minus a. This will become x minus a. So it is fa plus this fa plus f dash a into x minus a, and then this is in this case f double dash will come out. This f double dash will come out. You will get now. What will you get? Let us see. Then first we write fx. This fx is equal to fa. Fx is equal to fa first term. At least we can write them easily. Fx is equal to fa plus now second term. Second term is f dash a x minus a. Yes, f dash a x minus a. Good. Plus third term. What is third term? Third term is you take this f dash a out because it is constant. You will be left with this third term will be double integral and into dx. Integral a to x, then sorry f double dash a out, a to x dx plus third term, sorry, this is our last term, perhaps. Yes, this is our last term. Third term is triple integral f triple x dx cube, triple integral a to x f triple x dx cube. It's important to realize that what this the order of the integral. For example, this is triple integral 3, this 3, all are same. Now we can now looking at this now, you will integrate dx. The problem is like this. You have fx is equal to fa plus f dash a x minus a plus now plus f double dash a. Now you have, let us first evaluate this integral. The integral will be ax. Forget about this, just focus on this a to x dx. Integrate this much. This will give you a to x dx will give you x minus a. Simply because integral dx is equal to x, and when you have limits a to x, this will result in x minus a, because when you give value x to x, you will get x. When you get a, you have this a. So it is this is equal to x minus a. Remember this is a x minus a. Okay, now x minus a, and then we should have second dx there because we had two integrals. But why did we drop that second dx? Let us see here why we had that and how did we actually drop that second. So you have a to x here, and inside that you have f double dash a, then f triple dash a. Actually, yes, actually this is the originally it was correct. When I had written it as a double x, then it was actually this was correct. What that means? It means that this dx square was common to both this and this. Common to both. You can check it easily. No problem. You won't face any problem at all. So if you see it now, you have f double dash a, and then it has two dx's. These two dx's with that. 3 dx's. This will now have 3 dx's because of this. And when we do this correction here, we have dx into dx. Okay. Then one dx I have consumed. The other dx is there. I have consumed one dx when I evaluated this. When I evaluated this much, I consumed 1. But the other is ax dx. Ax, what is the value of this? The value of this is x minus a. I mean value of this encircled, this part is x minus a, and into dx, into this dx. this dx is there. Plus third is ax integral ax f triple dash x. F triple dash x is, we will keep it as it is, f triple dash x dx cube. Finally, we have now next page. We have fx is equal to. Let us collect the terms till now. What are the terms? Fx is equal to first term is equal to fa. So fa. Second term is equal to, and let us go back and see. Second term is equal to f dash a x minus a. F dash a x minus a. F dash a x minus a. X minus a. This is the second term. Third term is equal to, not third. Third term is this. F dash a. You have to integrate now x minus a with respect to x. That is simply x minus a raised to 1, x minus a raised to 1, raised to 1 plus 1, 2, divided by 2, this much. This will be, when you evaluate it, it will be this, x minus a raised to divided by 2. And if you take the limits x and a, you simply get this x and a. Put x here, a here. You will simply get this x minus a whole square divided by 2. X minus a whole square divided by 2 after integrating this and substituting the limits. So you will have this term x minus a, first f double dash a into x minus a whole square divided by 2. Then next we have next term is this triple integral a to x triple integral, a to x now a to x 3 times, and then triple integral f triple x this integral triple third order derivative into dx cube. Naturally, you know now the course, and we can easily now write its other these functions, these terms quite easily we can write it. For example, if I add the fourth term, then it will be ax fourth ax into f4x dx cube. Now see it, now there is one more thing. Look here, it is, you have here fa, that is fa is the yes, let's do this thing now. Let's do it, write it here. fa plus f dash a into x minus a, okay, into x minus a plus f double dash a by 2 x minus a whole square plus, then we will have f triple dash a by 3 factorial whole x minus a whole cube, because you know, let me see, you can check it with by x taking one more this by using fundamental theorem of calculus once more for this f triple dash x. Now you will have finally, the final term will be, if I take now final term, but before final term I will have this fn minus 1, that is n minus 1th derivative of the function evaluated at a divided by n minus 1 factorial then you have x minus a whole raised to n minus a. Now the nth is this, and nth here will be a term where you have how many these integrals, n integrals. I will write them shortly as ax dot dot dot, and it is shortly, and I have f n x, f n x. Now nth order, this derivative f n x dx raised to n, dx raised to dxn. This term, this last term, this is the last term. This last term is written as it is called a remainder, or n. We write it or nx. Or nx is this term. Integral ax dash 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 integral a to x dash dash, then fnx fn x divided by n factorial. Yes, it was, we had to divide it by n factorial. It was like this, n factorial. Not actually, we have not actually integrated it. We have simply to write it like this, fnx into dx raised to n, dx raised to n. You should not write it anything else here. So this is this we call the remainder. If we call it remainder, what is the rest of the expression is this without remainder is this rest of the expression. That is simpler to show. That is, one is, first is fa, then you have f dash a into x minus a, then f double dash a by 2 factorial into x minus a square, then f triple dash a 3 factorial x minus. You can now easily write it. We have first fa, value of the function at a, then we have f dash a x minus a, then we have f double dash a x minus a whole cube, and we have here we have 2 factorial, and we have x minus a whole square plus plus dash 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 plus lastly fn minus 1 a divided by n minus 1 factorial, n minus into x minus a raised to n minus 1 plus remainder plus or n x, remainder as defined by this. Now this is what we call Taylor's formula. It is called Taylor's formula. If we let n tend to infinity, if n becomes very large, the number of terms included in the series, if that number becomes very large, and in that case if we assume that r and x also becomes very small and we can ignore it, then we write this without r and x is then called Taylor's series. That is called series, where we have infinite terms. Taylor's series is an exact thing. If we take infinite terms, it will never. There are some questions actually that will naturally come up. For example, if we have an infinite series, does it converge? And more. For example, about this r and x, what to do with this reminder? What we have to do with it? How can we handle it? This will be my topic in next video. Thanks. Till then, you try to understand it. You try to practice it so that you don't face any problem. I hope that there is no problem in deriving this. Thank you so much.